China launches groundbreaking 3-satellite constellation pioneering Earth-Moon space exploration. Date, April 16, 2025. Location, Beijing, China. On April 16, 2025, the Chinese Academy of Sciences (CAS) announced a monumental achievement in space exploration: the successful establishment of the world's first 3-satellite constellation in the Distant Retrograde Orbit (DRO) within the Earth-Moon region. This innovative development is anticipated to significantly advance future lunar exploration and the broader utilization of cislunar space. Background and development timeline. The groundwork for this ambitious project began in 2017 when the CAS initiated research into the Distant Retrograde Orbit (DRO) and its potential applications in space exploration. Recognizing the strategic importance of DRO for lunar resource exploitation and long-term human habitation beyond Earth, a detailed plan was laid out in February 2022 to develop a 3-satellite constellation dedicated to exploring the Earth-Moon space. The mission commenced with the launch of the experimental DRO-L satellite on February 3, 2024, which was placed into a sun-synchronous orbit to begin its experimental mission. However, a significant challenge arose on March 13, 2024, when the DRO-A and DRO-B satellites launched from the Xichang Satellite Launch Center in Sichuan Province encountered an anomaly that prevented them from reaching their intended orbit. After extensive troubleshooting including emergency maneuvers, the satellite team successfully placed DRO-A and DRO-B into their designated orbits by July 15, 2024. The constellation was officially formed on August 28, 2024, when DRO-A and DRO-B established communication links with DRO-L, marking a critical milestone in the mission. Key achievements of the constellation. Distant Retrograde Orbit DRO advantages. DRO is characterized by its low fuel requirements, making it an ideal hub for supporting missions between Earth, the Moon, and deeper space. The orbit allows for extensive scientific research and operational cost reductions, which are pivotal for future space exploration endeavors. Innovative technologies. 1. Low-energy insertion. The project achieved a world first by enabling low-energy insertion into DRO using only 1/5 of the fuel typically required for such maneuvers. This breakthrough drastically reduces the costs associated with accessing cislunar space. 2. Inter-satellite communication. The satellites successfully established K-band microwave inter-satellite communication links over a distance of 1.17 million kilometers, overcoming previous technological barriers in satellite constellation construction. 3. Space-based orbit determination. The satellites employed a pioneering space-based orbit determination system, allowing one satellite to accurately track another. This method achieved precision comparable to traditional ground-based tracking while significantly reducing operational costs. Strategic importance and future prospects. The establishment of this 3-satellite constellation represents a strategic leap in cislunar exploration, emphasizing the importance of DRO for lunar resource exploitation and long-term human habitation beyond Earth. The CAS highlighted that the Earth-Moon region, extending outward from near-Earth and near-lunar orbits, offers vast opportunities for space science exploration, infrastructure deployment, and crewed deep space missions. The implications of this project extend to various scientific fields, including astrophysical research, where it supports investigations such as gamma-ray burst detection, and technology trials like atomic clock operations. Furthermore, the satellites are expected to enhance future lunar exploration missions by providing space-based inter-satellite measurement and autonomous navigation services. Common themes across sources. Reports from multiple sources consistently emphasize the strategic significance of the DRO constellation for cislunar exploration and the technological innovations that make it possible. They highlight the breakthroughs in satellite technology, orbit determination, and the potential for extensive scientific research. Conclusion. China's successful launch of the 3-satellite constellation in the DRO marks a significant milestone in space exploration. With innovative technologies and strategic foresight, this project not only enhances China's capabilities in space but also contributes to the global understanding of cislunar space dynamics and exploration potential. As researchers continue to explore the complexities of the Earth-Moon region, the foundation has been laid for future missions to the Moon and beyond, promising exciting advancements in our quest to explore the cosmos. China's recent establishment of the first 3-satellite constellation in the Distant Retrograde Orbit DRO presents several counterintuitive aspects that challenge conventional assumptions about space exploration and satellite technology. 1. Efficiency of low-energy maneuvers. One of the most surprising achievements from this program is the ability to enter the DRO using only 1/5 of the fuel typically required. This contradicts the common belief that more energy or fuel is necessary for complex orbital maneuvers, particularly when dealing with the gravitational influences of both the Earth and Moon. The innovative design concept of this mission suggests that strategic planning can significantly reduce fuel consumption, highlighting how advanced engineering can lead to unexpected efficiencies. 2. Inter-satellite communication over traditional ground tracking. The successful establishment of K-band microwave communication links between satellites at distances of over 1.17 million kilometers adds a layer of complexity to our understanding of satellite operations. Traditionally, ground-based systems have been essential for tracking and communication. The idea that satellites can autonomously communicate and track one another with precision equivalent to traditional methods within just 3 hours of data challenges the assumption that ground stations are indispensable for accurate orbital navigation. This technological leap suggests a future where satellite constellations can operate more independently, reducing reliance on terrestrial infrastructure. 3. Cost reduction in deep space exploration. The combined achievements of low-energy insertion and satellite-to-satellite tracking significantly lower operational costs associated with deep space missions. This runs counter to the narrative that deep space exploration will always incur high costs due to the complexity and risks involved. By demonstrating that operational efficiency can be achieved through innovative design and technology, China's advancements could democratize access to space exploration, making it viable for more nations and private entities. 4. Strategic importance of DRO. While the DRO is recognized for its stability and low fuel requirements, the strategic implications extend beyond mere orbital mechanics. The notion that this orbit could serve as a hub for extensive scientific research and commercial activity in cislunar space is an unexpected pivot in space strategy. This challenges the traditional focus on immediate lunar surface missions and emphasizes a broader vision of utilizing the space between Earth and the Moon as a dynamic area for exploration and resource utilization. 5. Potential for commercial exploitation. The establishment of a satellite constellation in DRO opens avenues for commercial activities, which is a departure from the historical view of space exploration as a government-only endeavor. The idea that private entities could leverage this technology for lunar resource exploitation or other commercial ventures suggests a shift in how we perceive the future of space activities, blending governmental and commercial interests in unprecedented ways. 6. Application in fundamental science. The research potential unlocked by the constellation, including gamma-ray burst detection and atomic clock operations, contradicts the expectation that deep space missions are primarily focused on exploration and resource acquisition. Instead, this initiative highlights that such missions can also contribute to fundamental scientific advancements, proving that exploration can yield significant scientific returns, thus enhancing the value proposition of investing in space endeavors. 7. Redefining lunar exploration. The traditional view of lunar exploration often focuses on landing missions. However, the establishment of a DRO-based satellite system indicates a shift toward a more integrated approach to lunar exploration, where orbital missions play a crucial role in supporting surface operations. This challenges the assumption that successful lunar missions must culminate in landings, suggesting that orbital platforms can be just as critical for comprehensive exploration strategies. These counterintuitive insights from China's three-satellite constellation initiative challenge established narratives in space exploration and technology, suggesting a future where innovative engineering, strategic foresight, and collaborative efforts redefine the boundaries of what is possible in cislunar and deep space exploration. The recent announcement by the Chinese Academy of Sciences (CAS) regarding the establishment of the world's first three-satellite constellation in a distant retrograde orbit (DRO) within the Earth-Moon region represents a significant leap in space exploration. While many aspects of this report have received coverage, there are several critical elements that may be overlooked yet hold substantial significance for both the future of space exploration and international space policy. Key overlooked aspects. 1. Strategic implications of DRO. The distant retrograde orbit is not merely a technical achievement, it has strategic implications for space exploration. The DRO allows for a stable platform for various missions, including lunar resource exploitation and deep space exploration. The significance of this is rooted in the increasing global interest in cislunar space as both a resource hub and a staging ground for further interplanetary missions. As nations and private entities start to eye the moon and beyond for resources, having a foothold in a stable orbit like the DRO could provide significant advantages in future missions. 2. Cost efficiency in space missions. The successful demonstration of low-energy insertion into the DRO utilizing only 1/5 of the fuel typically required is a game-changer for cost efficiency in space missions. This innovation not only lowers the financial barrier for sending missions to the moon but also encourages more frequent and ambitious explorations. The reduction in fuel requirements can lead to more payload capacity for scientific instruments or even human passengers, thereby expanding the scope of missions that can be undertaken. 3. Technological innovations. The establishment of K-band microwave inter-satellite communication links over a distance of 1.17 million kilometers is a significant technological milestone. This advancement facilitates real-time communication and data transfer between satellites in cislunar space, which is crucial for coordinating complex missions and enhancing the reliability of satellite constellations. The ability to maintain communication in such vast distances is essential for future exploration, including potential crewed missions or automated lunar bases. 4. Satellite-to-satellite tracking system. The innovative space-based orbit determination system that allows one satellite to track another, achieving precision that typically requires 2 days of ground-based tracking, is a monumental shift in how satellites can operate in cislunar space. This capability not only improves operational efficiency but also reduces the dependency on ground stations, which can be limited by geographical and atmospheric conditions. This new tracking method can significantly enhance the reliability and responsiveness of satellite operations, allowing for quicker adjustments and improved data collection. 5. Broader scientific research opportunities. While the report emphasizes the constellation's potential for astrophysical research, including gamma-ray burst detection, it also hints at the exploration of fundamental scientific questions in fields like quantum mechanics and atomic physics. The potential for conducting high-precision experiments in the unique environment of cislunar space could yield discoveries with implications far beyond our current understanding. This aspect of the project may not receive enough attention, but it highlights the constellation's role in advancing human knowledge. 6. Global space policy and collaboration. The establishment of this satellite constellation raises questions regarding international cooperation and competition in space. While China's advancements in space technology are significant, they may prompt responses from other spacefaring nations, leading to a new era of space policy, including potential treaties or agreements regarding the use of cislunar space. The implications of this development on global space governance and the potential for collaborative missions in the future could be transformative. Yet these discussions are often overshadowed by the technological achievements themselves. 7. Long-term human habitation. The strategic significance of DRO for long-term human habitation beyond Earth is a critical point that might be overlooked. As missions to establish human presence on the Moon gain traction, having a reliable staging area in a DRO could facilitate not just lunar bases but also missions to Mars and beyond. This aspect ties into global considerations about sustainability and the ethical implications of space colonization, which are vital for shaping future policies. Conclusion. In conclusion, the establishment of China's three-satellite constellation in the distant retrograde orbit is a multifaceted achievement that extends beyond technical prowess. The overlooked elements, such as the strategic implications for future lunar and deep space missions, the cost efficiencies realized, technological advancements in satellite communication and tracking, and the broader opportunities for scientific research, are all significant in shaping the future of space exploration. Furthermore, the geopolitical and policy ramifications of this advancement warrant careful consideration as nations navigate the new frontier of cislunar space. Recognizing these aspects can provide a more comprehensive understanding of the implications of this milestone in space exploration. 1. Establishment of the Distant Retrograde Orbit DRO constellation. China's successful creation of the world's first three-satellite constellation in the Distant Retrograde Orbit DRO marks a significant advancement in space exploration. This orbit serves as a stable hub for future lunar missions and deeper space exploration. The DRO's unique characteristics allow spacecraft to maintain their positions with minimal fuel, thus reducing operational costs and enhancing the feasibility of extensive scientific research. The strategic importance of this development cannot be overstated, as it lays the groundwork for resource exploitation on the Moon and supports long-term human habitation beyond Earth. 2. Technological innovations and breakthroughs. The project highlights several groundbreaking technological achievements. Notably, the satellites utilized a method that required only 1/5 of the fuel typically needed for entry into the DRO, representing a major advancement in energy efficiency for space missions. The establishment of K-band microwave intersatellite communication links over a distance of 1.17 million kilometers demonstrates significant progress in satellite technology, overcoming previous limitations in constructing large-scale constellations. Furthermore, the introduction of a space-based orbit determination system that allows one satellite to track another efficiently reduces operational costs and improves mission effectiveness. 3. Scientific research potential. The three-satellite constellation is poised to facilitate extensive scientific research, including studies on astrophysical phenomena such as gamma-ray bursts and trials for advanced technologies like atomic clocks. The stability and positioning of the DRO will enable scientists to conduct fundamental research in various fields, including quantum mechanics and atomic physics. This capability opens up new avenues for exploration and experimentation in cislunar space, fostering a deeper understanding of both the Moon and the broader solar system. 4. Strategic implications for future exploration. The successful deployment of the DRO constellation enhances China's position in the global space race and underscores its commitment to advancing space exploration. The project not only strengthens China's capabilities for future lunar missions but also positions the country as a key player in the potential commercialization of cislunar space. The ability to establish efficient communication and navigation systems in this region could support a variety of commercial activities and international collaborations, thus shaping the future of space exploration and utilization on a global scale. 1. The Apollo Program 1961–1972. The United States Apollo program was a series of missions aimed at landing humans on the Moon and bringing them safely back to Earth. The program is best known for Apollo 11, where astronauts Neil Armstrong and Buzz Aldrin became the first humans to set foot on the lunar surface on July 20, 1969. The Apollo missions not only achieved the landmark goal of lunar exploration but also expanded our understanding of space travel, lunar geology, and the potential for human habitation beyond Earth. 2. The Soviet Luna Program 1959–1976. The Luna program was a series of Soviet robotic spacecraft missions that aimed to explore the Moon. It achieved several milestones, including the first human-made object to reach the Moon, Luna 2, the first successful soft landing on the Moon, Luna 9. and the first sample return mission from the Moon Luna 16. The program demonstrated key technologies for lunar exploration and laid the groundwork for future robotic and crewed missions. 3. Mars Exploration Rovers 2004-present. NASA's Mars Exploration Rover program, which includes successful missions such as Spirit and Opportunity 2004, Curiosity 2012 and Perseverance 2020, has significantly advanced our understanding of the Martian environment. These rovers have conducted extensive scientific research including geology, climate and the search for past life. The program has pioneered technologies for remote exploration and autonomous operation, much like the innovative satellite technologies employed in China's recent 3-satellite constellation. China's recent establishment of a 3-satellite constellation in the Distant Retrograde Orbit (DRO) marks a pivotal moment in space exploration, particularly in the Earth-Moon region. This ambitious project not only showcases China's technological advancements but also sets the stage for future lunar missions and broader space exploration initiatives. Predictions for the future of space exploration and cislunar activities. 1. Enhanced lunar missions. The successful deployment of the DRO satellite constellation will likely lead to more sophisticated lunar missions. With a stable and low-energy orbit, China is poised to conduct extensive scientific research on the Moon, including potential resource extraction and the establishment of permanent bases for human habitation. This could result in more frequent and longer missions to the lunar surface, facilitating human exploration and possibly even lunar settlement by the 2030s. 2. Cislunar economy development. The strategic location of the DRO as a hub for cislunar activities will foster the growth of a new economy in space. This includes commercial endeavors such as mining lunar resources, developing space tourism, and creating infrastructure for satellite constellations that provide services such as communication and Earth observation. The cost reductions achieved through innovative technologies in entering DRO may encourage private investments and international collaborations in these ventures. 3. International collaboration and competition. As China expands its capabilities in cislunar space, other nations may accelerate their own lunar programs, leading to increased competition. This could spur collaborative efforts in areas where interests align, such as planetary science, environmental monitoring, and technology development. However, it may also lead to geopolitical tensions over resource claims and space governance, necessitating new international treaties and frameworks. For technological advancements, the breakthroughs achieved in satellite communication and orbit determination are likely to inspire further innovations in satellite technology. Future satellites may employ similar low-energy insertion techniques, enhancing operational efficiency and reducing costs for space missions globally. Advances in satellite-to-satellite communication may also enhance navigation and data relay capabilities for deep space missions. 5. Scientific research and discoveries. The scientific potential of the DRO constellation includes astrophysical research such as gamma-ray burst detection and investigations into the lunar environment. As research continues, we can expect new findings that could alter our understanding of fundamental physics and astronomy. The unique conditions of the DRO may also allow for experiments that are not feasible on Earth or even in low Earth orbit. 6. Sustainability and long-term habitation. With an eye towards sustainable exploration, future missions may focus on utilizing lunar resources such as water ice for in-situ resource utilization (ISRU). This will be crucial for supporting long-term human presence on the Moon and could serve as a testing ground for technologies needed for future Mars missions. 7. Public engagement and inspiration. As China progresses in its space endeavors, public interest and engagement in space exploration will likely grow. This may lead to increased educational initiatives aimed at inspiring the next generation of scientists, engineers, and space enthusiasts. Public appreciation of space exploration can foster a culture of innovation and curiosity vital for the continuous advancement of technology. 8. Impact on Earth-based technologies. The innovations developed for space applications often find their way into terrestrial technology.
The advancements in satellite communication, navigation, and autonomous systems may lead to improvements in various sectors, including telecommunications, transportation,
and disaster management on Earth. Conclusion: China's pioneering 3-satellite constellation in the distant retrograde orbit heralds a new era in space exploration, offering numerous opportunities for scientific discovery, economic development, and international collaboration. As the nation continues to push the boundaries of its capabilities, the implications for cislunar space and beyond will resonate well into the future, shaping the next chapter of humanity's journey into the cosmos.